who's at ARIA and École Normale Supérieure, and he did his PhD at Berkeley almost 20 years ago, and since then I believe has stayed in Paris doing research on optimization and machine learning, and he also was awarded several prizes, among which there are an ERC starting and consolidator grant. And now we're looking forward to hearing a presentation on information theory with kernel methods.
Okay, so thanks a lot for the introduction. I would like also to thank the organizer for the invitation. So today I'm going to talk about probability distributions, and I'm sure many of you have used probability distributions, and in many cases you need to compare two of them. Okay, so here I give a few examples coming from data science, where I come from. So for example, if you have some data, you have a model, and one way of fitting the model to the data is by minimizing some sort of distance between the data and the model. So the classical statistical applications. Sometimes you want to quantify the loss of uncertainty. So I take some data, I add some noise to preserve privacy. I want to measure the amount of loss of information. In other areas, which I've worked quite a bit, is when you analyze some neural networks and you let the number of neurons go to infinity, you have an assembly of neurons, and then you can use probabilities to analyze how the neural network is converging. So this is a very classical subtask. So here I've just talked about data science, but there are many other applications. In most places you want to compare distributions. So why is it difficult and interesting is that when you want to use this in data science, you have to think of distributions on a large space, okay? Not in R2, but in potentially high dimensions, and dimensions could be, for example, like thousands or millions. And in order to compute those distances, often you need access to the distributions, and it's reasonably easy if you have discrete random variables or if you have Gaussians. But the difficulty comes from the fact that if you have like non-linear dependencies among your variables, which are not captured by a Gaussian variable, this can be hard. Third difficulty, you need to be able to estimate those from data. Okay, in the context of data science, I want to fit a model to some data. I need to be able to use the data to compute my distances. And finally, you want that distance to mean something. Okay, and if I have a distance of 1, what does it mean for my problem? So you want some physical meaning to that distance. So there are many ways of comparing probability distributions, and I divided them into like three main subclasses. The first one is using information theory. So this is like typically done when you set on which you do probability is finite, and this is a classical definition of the Kullback-Leibler divergence between two distributions P and Q over a finite set, where you sum over the elements of your set P log P over Q. So this happens to be like a non-negative. It's not a distance, okay, but it's one measure of dissimilarity. It has some nice invariance properties. Okay, so if you go to continuous random variables, it's invariant by reparametrization. It has some strong physical interpretation. Of course, in physics, okay, the entropy in physics, also in communications. Okay, this is essentially the loss in performance where you encode some data source which has a distribution P by a coder which is optimized for distribution Q. Then you lose a bit in terms of the optimal performance. It's the loss of information. Okay, so this is a distance a measure which has nice interpretations. If you do statistics or probabilities, this comes up all the time. Okay, the entropy is used in many places. The issue here is that in my context of data science, if I want to estimate that from data, it's quite hard. Okay, I need to estimate the density, and this is often difficult. The other key class of distances is the optimal transport distance. Okay, this you can make it a distance here, where it does have some physical interpretation of moving some mass around, but the value itself is not key it's not easy to understand, and this is very important. And it's not invented by Gabriel Perret and Marco Couturier, but they have a nice book about it if you want to know more about it in terms of computations and use in data science. So what I want to focus on today is on distances which are based on moments. So what is a moment? Is you take a feature phi, which goes from your input space x to some Hilbert space. You can think of, if you prefer, RD, if you prefer. And we're going to consider what is called the mean element, mu p, which is the expectation under p of your feature phi. So for example, if phi of x is, if you are in R, if phi of x is x, x squared, x cubed, you get all the classical, like all the classical moments. So what is nice is that if you take sufficiently many moments, you need infinitely many of them if x is infinite, then it does characterize fully the distribution. And there is a very natural notion of distance with those moments because I've equipped my feature map phi, but the image of phi with a Hilbert structure. So if I take the Hilbert norm mu p minus mu q, okay, I get a natural metric over distributions. So this is often called the mean MMD, maximal mean discrepancy. And the key here is that if you have access to data, so IID, like independent and asymptotically distributed data for P, and same thing for Q, there's a natural estimator for that thing, which is essentially you form mu p hat, which is the average of the features that you observe, where xi here I assume to be the ID data corresponding to P. You take similarly the ID data yj, which is sampled from Q. This is mu p hat, this is mu q hat. You take the difference, and this is the natural estimator. So the key and thing here is that although phi could be in infinite dimensions, the convergence rate of that estimator is 1 over root n, meaning that the difference between this guy and this guy is only of order 1 over root n. Okay, this is somewhat surprising because in infinite dimensions you may have like this may not be true, but this happens to be true here. So this has a good property in 1 over root n, and it can be computed only knowing the dot products, okay, of phi x and phi y. So why is this important? This is important because it's hard to manipulate like Hilbert space elements in a computer, okay? And so if I take this formula and I expand the square using the dot product, I will get a bunch of dot products between phi of xi and another phi of xi, or phi of xi and phi of yj. So at the end, what I need to know is how to compute all of those dot products, and this is often called a kernel. And if this one is easy to compute, and I will show examples in a moment where phi here is infinite dimensional, but k is easy to compute, then you can compute this in typically quadratic time in n and m. Okay, so this is a classical, like using moments to characterize distributions. The issue, this has been used like in many applications, other ones I have mentioned earlier. Yep. So x, no assumptions on x. Big X, nothing. Can be anything. Little l, n. Oh, so this is data given to you. So I give you data, okay, and data given to you with a certain number of observations, and n is the number of observations for the distribution P, and m for the distribution Q. So here, and this is one of the key benefits of that framework, is that this can be applied to any set X as long as you can define some feature map and some kernel. All right. So the issue here is that although this has been used quite a lot, there is no, it's not linked to information theory. Okay, so it's Hilbert, it's mu p minus mu q, so it's nice, symmetric, but it cannot be used. It cannot be used as a placeholder for entropy in other setups. So the goal of today will be to show that you can modify a bit that framework. Okay, you want to preserve all of those nice properties, meaning that It can be estimated in a rate 1/√n, because this is important if you want to apply this in practice, and it has a link with information theory. So the way it's going to be done is by not only considering like moments of phi, but moments of matrices defined by phi. Okay, so define phi of x times phi of x star. So in the finite dimension, this will be like if phi of x lives in Rd, this is a d by d matrix. Okay, phi of x times phi of x star. So I say star because phi of x can be complex, as I can show in a moment. So star is conjugate transpose here. And by having the expectation of phi of x times phi of x star, you go from an element of H to an operator on H, and that operator is Hermitian and positive semi-definite, okay? Because phi times phi star is itself Hermitian positive semi-definite. And then we're going to use something different than the difference between mu p and mu q. We're going to use some quantities which are closer to information theory, namely the von Neumann entropy and the associated relative entropy. Okay, and applying these to this will be the main topic of the talk. Okay, and what we will see today is that the properties which were true from the slide above for the mean element will be true as well here. There will be first a clear relationship with the regular information theory, estimation in 1/√n, and we'll see like at the end of the talk like relationship to Warshall inference. So now let's look. This is the summary slide of the talk. I'm going to do that in the next half hour. So let's put some assumptions on the problem. Okay, so the set X can be anything. Okay, I will often use the cube 0, 1 to the d as an example. I'm going to assume that I know some positive definite kernel. So what is a positive definite kernel? It's a function on x times x for which all matrices of pairwise evaluations are positive semi-definite. Okay, so if I take x1 to xn and I form the matrix k of xi xj, it's n by n matrix, this has to be PSD. So I'm going to assume X is compact for simplicity, and I'm going to assume that the kernel is normalized. And in fact, I will mostly use equal to 1 to make my life simple. So what is known about like those like positive definite kernel is that in fact they are all dot products. Okay, so in the slide above, I started from phi and I defined the kernel. It can go like in the other way. For any k which is PSD, no, for which all matrices of pairwise evaluations are positive semi-definite, then you know there exists a feature map phi that go from set X to some Hilbert space, so that k of xy is phi of x dot product with phi of y. Okay, so this is like a theorem shown by Aaron Jean in 70s, I guess. And the way it is often used in practice is by looking at functions f of x which are linear in phi of x. Okay, and for example, if you take a Sobolev space, okay, of order which is sufficiently high, then you can show that that set of function can be represented as f of x as being a dot product between an element of the Hilbert space and some phi of x. So what I will need in my talk to fully characterize a distribution is that the kernel is big enough. Okay, as I've mentioned in the previous slide, if I want to characterize the probability distribution, I need phi of x to be of large enough dimension. Okay, and typically infinite if x is not finite. So this, in the language of kernel, this means I have to have a universal kernel, meaning that that set of function has to be dense in the space of continuous functions. So for example, Sobolev functions, okay, are dense in the space of continuous function. So the classical example that you see in practice, I've mentioned like the Sobolev space, okay, and often in practice we use a so-called Gaussian kernel, which is the exponential of minus the square distance over sigma square. So sigma here is a bandwidth parameter, okay, telling you that if sigma is large, I'm going to consider like a small range interaction. Now, if sigma is small, I'm going to consider small range interactions, and if sigma is large, larger range interactions. And this kernel, it's not obvious, but corresponds to when you look at all the phi of x, which is here implicit, okay? We never know what phi of x is. We know it exists, and we know that those linear functions in phi of x happens to be infinitely differentiable functions. This is a setup for now. All right, so to make this concrete, in the rest of the talk I will use a torus, so 0, 1 to the d, so 0, 1 to the d with like periodicity conditions, and I'm going to consider kernels which are invariant by translation, that only depends on the difference of x between x and y, and with q being one periodic, okay, I want to leverage the periodic structure of the torus. In that setup, it's known that, it's Buckner theorem, that the kernel K is positive definite if only if the Fourier series of Q is non-negative. Okay? And you can explicitly build a feature map, which is like indexed by omega, an element of ZD, by simply taking the square root of the Fourier series. So here, the Fourier series is positive, so I can take the square root, times the complex exponential. So why is this the case? Because if I form the dot product, okay, so I sum over omega, phi of x of omega times phi of y of omega transpose, I end up by forming the sum, I get this ends up being that, and then this with the transpose ends up being the complex exponential, and now I have the sum of the Fourier series, and I get back the function. Okay, so this is just an example of a explicit feature map. Phi is infinite dimensional, so I cannot manipulate phi because it's in ZD, but I can manipulate the kernel. So as an example, and more, if now I look at what my covariance operator is, then if I write the element omega times omega prime, I get the scaling terms plus an expectation of a complex exponential, which is exactly the characteristic function taken at 2 pi omega minus 2 pi of omega prime. So in a sense, all of that covariance operator is a way to put the characteristic function in a matrix. Okay, so you take all those elements, and you put them in a matrix. Okay, and this is your covariance operator. Later in the talk, I will use, like as a concrete example, the q out of omega, which is an exponential. Okay, and for which you can find q in closed form. Okay, so I won't give the formula, but there is a q in closed form for that example. So another important set is the finite set. Okay, so all the starting point is using like information theory on finite sets. So let's be sure that finite sets are included in the framework. So if I take the finite set X, which is like with m elements, and if I use a so-called one-hot encoding, where I send every element to the one of the canonical basis vectors, so essentially phi of x is of dimension m, and the ith component of phi of x is 1 if x is equal to I, then you can check that phi of x times phi of x star here is a diagonal matrix, and that sigma p happens to be diagonal with p, the probability mass function on the diagonal. So essentially, this is a very expensive way of characterizing like a probability mass function by putting them in the diagonal. You can go further by adding like x being like more complicated, having a factorial structure, but I won't go there today. But of course, it goes beyond, and the whole area of kernel methods is meant to construct like feature maps and kernels for complex objects. So if you give me an image, a molecule, a text document, I can compute kernels and I can apply those techniques. Well, so a few properties, okay, of those covariance operators. So by design, sigma p is a positive semi-definite because it's the expectation of a PSD operator. Hence, it has a trace which is less than 1 because phi of x has a norm less than 1. So here I'm surfing along the details of operators, but believe me, this can be made formal. You get a sequence of positive eigenvalue going to 0. And because I have assumed that my kernel is universal, so for example, my Fourier transform, my Fourier series is strictly positive everywhere, then the mapping from P to sigma P is injective. So I do characterize my distribution, which was the original goal. So for the moment, I've done nothing more than replacing phi of x by phi of x times phi of x star and using the same theory. Okay, at the moment, I've not used the matrix structure of or the operator structure of my problem. So let's do it now. I'm going to consider what is called the von Neumann entropy, which is essentially the sum of all lambda log of lambda for lambda eigenvalues of my operator A. Okay, so it's a spectral function, which is often written as trace of A log A. So what is known about that function? So first, it's a convex function because it has all like a convex spectral function, where if I were to replace here lambda log of lambda by any function of lambda which is convex, I will get a convex function. So trace of A log A is convex. As a convex function, I can compute its Bragman divergence. So what is a Bragman divergence? This is if I get a convex function psi of A, at any given B, I can build the tangent, okay, at B, which is built from the gradient, okay, and this is a 0th order term, this is a linear term, and then because I'm convex, psi of A is above its tangent, and the deviation, the distance between the function and the tangent is called the Bragman divergence. It's always non-negative, and if the function psi is strictly convex, which is the case here, then it's an if only if. So the d of AB is 0 if is strictly positive, no, is equal to 0 if only if A is equal to B. Okay. So this is going to be what is called the relative entropy, okay, because it starts to look like the KL from before. So the KL was the sum of P log P over Q. Now I get the trace of A log A. You would like to say log of A minus log of B is log of A over B, but it's not possible for matrices, but this is in principle the same. So what is known about those objects? So those objects have been studied a lot by physicists, okay, for quantum mechanics. So a few properties, some of them are easy, some of them are not. The first one I've mentioned already. This is already true because D of AB is a Bragman divergence, so that property is straightforward from convex analysis. Another easy one is it's convex in A. Why? Because trace of A log A is convex. That part in A is linear, so it's convex. So it's convex in A. The non-trivial part is a joint convexity in A and B. This one is a tough one, okay, and the proof of which is quite involved. And so this is jointly convex. I'm going to use it in the next slide. And this has been used already in quite a number of areas. So for those of you who like concentration inequalities for matrices, there's a very nice book by Joel Trop, where essentially the starting point is really the joint convexity of that relative entropy. Okay? It's also used in optimization, okay, as a way for doing smoothing. So how can we use it? Okay, so we're going to now use it with A and B being sigma P and sigma Q. So I have two distributions, P and Q. I compute the covariance operator for P, sigma P, the one for Q, sigma Q, and I look at the relative entropy between sigma P and sigma Q. So this is the definition. So a few properties. It's finite under like simple conditions. Okay, I don't want to spend too much time on that. It's always non-negative, almost by construction, equal to 0 if only if sigma P is equal to sigma Q. And because I've assumed that the mapping from P to sigma P is injective, this is also only true when P is equal to Q. One extra thing, it's jointly convex in P and Q. Okay, why? Because D is jointly convex in A and B. And since A and B are linear in P and Q, I get joint convexity. So here, I'm only considering the relative entropy, and you could extend this to entropies, and you can look at the paper if you want to know more. So first, as a spoiler, I'm going to preserve many properties of the classical entropy, but not all of them. Why? Because if I preserve all properties of the entropy, I have to be the entropy, okay? And I'm going to miss one, And you can ask me after the talk which one I'm missing, okay? But it's related to conditioning, but it's not the goal of today to spend too much time on that. But it's going to miss a few properties of the entropy. All right, so let's start simple. Let's look at the finite set X. So as you remember, as I told you a few slides ago, if you use a one-hot encoding, you're putting the probability mass function on the diagonal. So all the spectral functions will be easy to compute. Everything commutes, okay? And then you can simply like look at the diagonal and sum over the diagonal. And now what you recover is that the kernel entropy for that simple setup of like a one-hot encoding, and this extends to all orthonormal embeddings, then you recover exactly the Shannon relative entropy. Okay, so this is in fact the starting point in many like quantum information theory paper. You want to make sure that you go back to the regular entropy when you have a finite set. The key question is, what about what can you say beyond finite sets? So this is what I'm going to show is that regardless for all problems I've considered so far, you always get a lower bound on the true entropy. So let's take a proof, and it will be like a direct application of Jensen's inequality. So I'm considering my feature map, which is bounded. This will be the only assumption here, on top of measurability and so on. So I'm going to define the relative entropy. This is the definition of sigma p. This is sigma q once I write it as an expectation over p. This I have to introduce the density of q with respect to p. And now what I have here, I have a function d, which is jointly convex, taken at an expectation over p of something and over p of something. So now I can use the joint convexity of the relative entropy by simply by seeing this as the expectation over p of the function d. Okay, so just a Jensen's inequality. And now I can look closely at my two operators. Those two operators are both rank 1, okay? So with most eigenvalues equal to 0, and one eigenvalue which is here the norm of phi of x square, and here the norm of phi of x square times the density here. Moreover, the eigenvectors are aligned, so at the end I can only do the computation over that single eigenvector, which is non-zero, and I get that formula. Okay, this is the eigenvalue of that matrix, and this is the so this is p log p over q. Okay, so this is a p part, this is a q part, and now if I reassemble, okay, I can remove the phis over there. Use now the fact that phi is equal to 1 to get exactly the Shannon entropy. Okay, so this is a very simple computation to show that I was able to obtain a lower bound of the entropy. Okay, so if sigma p, if you have a finite set, it's equality. Here it's only a lower bound. The question is how tight is it? And this is something which we can look at. And what you can show is that if you take two p and q which have like a strictly positive and regular densities, then the difference between the true entropy and the one I'm defining will be bounded. It's bigger than 0 because of the lower bound, and it's upper bounded by two quantities. Okay, one that depends on p and q, that depends on the density of p, density of q, and the smoothness of p and q, plus some term that depends on how far k is to an orthonormal embedding. We know that if we have an orthonormal embedding, you get 0, okay, and this is just a characterization. So the proof, I won't go over the proof, but I just want to mention that the proof is using information theory in the quantum case, okay? So I had a proof of this, which was like 10 pages, and using a lot of formulas. And then you can simply here, let me just like gloss over the proof. You can just let me just mention this. Since this is quantum information theory, there are like inequality which is known for information theory. One of them is a data processing inequality. So if you take functions of random variables, you can only decrease the kernel divergence. And this is true in the quantum world. And you can design a measurement that will allow you to sandwich, to start from your entropy and define an entropy which is just a smoothing of the other entropies. So I won't give details, but just to highlight the fact that when you play with quantum entropies, you can use information theory to get bounds. All right, so now if you compute that big term delta k, then you can get interesting behavior. So if I take the kernel like q hat, which has a bandwidth parameter sigma, so this is true if I take the exponential, this will be true for other functions as well. The key that omega is always multiplied by sigma here. Then you can show that this term happens to be in O of sigma square. Okay, so there's no dependence in D in the power of sigma. There is a dependence in D in the big O, but there is no dependence. And typically, when you have the Fourier series which is of the form sigma over omega, the Fourier, if you take the Fourier transform, the inverse Fourier transform, you end up with a kernel which is of the form x minus y over sigma. So sigma is my bandwidth parameter. And so if sigma is closer and closer to 0, I get a better and better approximation of the entropy. So now let's look at the estimation from a finite sample. So as I've claimed in the beginning, I want to preserve that property. Okay, I want to be able to compute it for a finite sample. So here I'm going to focus only on that term, okay, the entropy term, and I won't look at the cross term. So what was true for the mean embedding? I replaced mu p by the mu hat of p, which was the average over my data of phi of x. So this is, I can do the same in that setup. A natural estimator of trace of sigma p log of sigma p is a trace of sigma p hat log of sigma p hat, where sigma p hat is a empirical covariance matrix. Okay, so I just sum over my data. So assuming that xi id from x, okay, I have n of them. I take the average of those. This is sigma p hat. So this I can define. Okay, but there are two issues here to look at. Can you compute it? Okay, because I'm still here in infinite dimensions. Okay, so I have a big operator. Can I compute its eigenvalues and sum them? Okay, and if I can, does it lead to a good estimator of trace of sigma p log of sigma p? It turns out that you can simply look at the eigenvalue of the kernel matrix. Okay, what is a kernel matrix? It is a matrix of pairwise evaluations. Okay, since I have a kernel, I know that this is like a positive semi-definite matrix. Okay, so with non-negative eigenvalues, and it turns out that that operator has the exact same eigenvalues as k over n. Okay, so this is exactly equivalent to saying that if I have a matrix phi, the eigenvalues of phi transpose are the same as phi transpose phi. This is just what I'm using here. So this can be done. And K now is an n by n matrix. So there is no more operators in infinite dimension. This is just a matrix of size n by n. So you can compute the eigenvalues in O of n cubed in terms of complexity. And this can be reduced if you want. Now, in terms of performance, okay, let's focus on that aspect. Then the key when you do statistics is to get estimators which converge like fast as n, by fast, at least converge when n goes to infinity. And what you can show is that between my estimator, which is random because my data are random, and my true quantity, if I take the expected absolute difference, it goes to 0 at some rates. Okay, so when n goes to infinity, let's focus on the first term, goes to 0 with some constant. Okay, and the key in statistics is to get to that constant. Okay, showing that it is finite and trying to characterize it. It turns out here that it can be characterized, and this is for the expert in the room. That quantity is often called the leverage score of my distribution. It's often used in kernel methods to characterize convergence, and it's happening there as well. And yeah. So in terms of proof, the proof is a bit involved, but the key starting point is you start from a log a, and you see log a at the integral of log t at the integral of 1 over t. So you can get a log a being an integral of a over a plus lambda identity. And now this is a tool on which you can start to do things, because you can use linear algebra and using classical tools from kernel methods to do that. All right. So let's look at my torus. Okay, so as my torus, you can compute C for the torus, and C happens to be proportional to sigma to the minus d. So now if I take only the dominant term, square root of C over n is sigma to the power minus d over 2 over root n. And now I can try to balance with the sigma square I had before. If my goal is to estimate the true entropy, then I know I have a bias, deterministic bias of sigma square, because I'm using a kernel. When I estimate, I pay the statistical error of this, and if I balance sigma square and that thing, I get a certain sigma, and then you end up with entropy estimation with the power of n, okay, which is like 2 over d plus 4. So what you see here is first that there is the classical curse of dimensionality. It's of power 2 over d essentially. So this means that if d is quite large, that power is very close to 0. So it's going down to 0 as n goes to infinity, but very, very slowly. Okay, and it's not far from optimal. Okay, so the optimal rate for that setup is just the square of that. So our goal was not to get an entropy estimate, but to end up with one which is reasonable. So in terms of so this you can apply. I won't give the. You can apply it in 1D here, but it applies to more dimensions as well. What I want to focus on for the last few minutes is on extensions. Okay. So why are we doing this? We're doing this either to compute entropies if you need them. Okay. So for example, it's a classical on the web. Particularly if you are Apple, will add noise to your data so that they can train on your data without revealing it totally. So they add noise, and you want to capture the loss of information, and this can be done by computing entropies. Okay, but you may want to use this use approximation of the entropy in places where entropy is used. And one important place is in inference for probabilistic model. So the starting point is a so-called like Donsker-Varadhan inequality. So if you give me any distribution Q on any set X and f a function from X to R, this is a log partition function. Okay, so here there is no minus signs. Okay, but it's the same here. So the log of the integral exponential f dq. So this is a normalizing factor for the distribution e to the power f. Then you can see it in a variational way as a supremum over all distributions p of the integral of f minus this K divergence. Okay, so this is like a starting point of many algorithms. Essentially, this is a duality between maximum likelihood and maximum entropy. And the key here, why is this used a lot in the probabilistic inference? It's used a lot because if your goal is to compute this, you can try to approximate that problem, okay? And if you get an approximation of that problem, this gives you information on that problem, okay? And this is what we're going to do. So now we're going to define, so replace d of pq by essentially my approximation of the relative entropy. And since this was a lower bound on the relative entropy, now I get an upper bound on the log partition function, okay? And this upper bound can be computed. Why? Because if I'm assuming that f is a quadratic form in phi of x, okay, then that piece is in fact can be seen as the trace of h times sigma p, where sigma p is my covariance operator. To know what I get is something which is entirely formulated through covariance operators, and this is linear in sigma p, this is convex in sigma p, and this under certain assumptions can be computed using like what is called semi-definite programming. So now with this new lower bound on DPQ, you get a new set of inference techniques for probability distributions. So I'm not going to give any detail, but this is something that we are currently working hard on. Other relationship, okay, in fact this was the starting point of this work, is what if you add some temperature epsilon? Okay, so this is the exact same slide as before, but I've added some temperature epsilon, okay, and I put back the epsilon there. This corresponds to putting an epsilon in there for the Dance curve Varadan inequality. So here, often when epsilon goes to 0, when temperature goes to 0, you're going to put all the mass in the minimizers of F, okay, and at the end, this quantity converges to the supremum of F, okay. So this is classical in the area of probability. What happens in my case? Okay, what if I replace dpq here by d of sigma p and sigma q? And it turns out that I recover, and this is like non-trivial, exactly sum of squares optimization. Okay, so what is sum of squares optimization? It's an area of optimization where you optimize over typically polynomials, and you see and use like the fact that if a polynomial is the sum of squares, it is non-negative. Okay, so this is a nice area like which was like launched by Joan and Pablo Parillo, and it turns out that if you let epsilon go to 0, you recover exactly that framework. Okay, not for polynomials but for infinite dimensional objects, which is a topic that we had started with my colleague Ale Rodi and our student Ulysse Marteau-Ferré. Just to highlight the fact that, like here, there is a relationship with optimization. Same thing there. There's a relationship with now sum of squares optimization. Other extensions. So if you don't like Kullback-Leibler, but you like Hellinger, Pearson or K-square, so all F divergences of that form, where F is convex, then everything goes through. Okay, so all the properties I've mentioned go through. Estimation gets a bit harder, but this can be done. The lower bound is the same. Okay, this is exact. In fact, this is the exact same proof. Also, if you work a bit in quantum information theory, it turns out that there are better quantum entropies than the one I've used. Okay, the one I've used is a classical one. But there is one which is a bit higher. Okay, it's not obvious. Okay, but this one. This is my log p over q, but done in the matrix way. This one, non-trivial, is jointly convex in A and B, okay, and always bigger. And since I'm having lower bound, the bigger the better, and this one is a bit better. All right, so a few last comments, okay. I often get the question, but aren't you just using Gaussians in feature space? Okay, that would mean that I send my data from X to H, and I do as if data were Gaussian. This is not the case because this is the entropy between two Gaussians, okay, of covariance sigma p and sigma q. It's not the same. It's not the same. And this one does not lead to links with information theory. Another interesting aspect: are there any link with quantum mechanics and information theory? I don't know. Okay, so in my proof, I'm using like some quantum reasoning. Okay, by using the data processing inequality. But if there are further links, I don't know. The key part here is that often in quantum mechanics, you only assume that sigma p is PSD and of trace 1. It's a density matrix. In my case, it has to be of that form. Okay, so it has to be in the span of all the phi times phi star. And in the example of like Fourier series, it had to be a Toeplitz matrix. It had to depend, so the value omega prime had to depend on the difference between omega and omega prime. So it was a very specific subset of density matrices. So I don't know if there are links or not. So to conclude, I've presented like some link between information theory and kernel methods, and the main tool was take the classical von Neumann relative entropy, apply it to a covariance matrix, and see what you obtain. And what you obtain is a well-defined lower bound on the entropy. This can be estimated with no optimization. Just take like an eigenvalue decomposition. And this has application to variational inference. So a few extensions. We're looking hard at having large-scale algorithms. Okay, because at the moment it's not ready for deployment with like very high dimensional data. At the moment we are constrained to have small data, but we are working hard on that. And we are currently starting a research program to really see how it performs compared to other ways of doing versional inference. And on this, I will thank you for your attention.
Thank you very much. Other questions or remarks or comments? So there's a very obvious one, which is which property of the entropy you missed?
Oh, I missed that. If you're in a finite data, you can see that h of the joint is h of the marginal plus the conditional of entropy. So h of xy is h of x plus h of y given x, and this is not true anymore. Okay, I cannot. Okay. It's not true. You cannot condition in an easy way. And if I had this one, I would be the entropy, and I miss this one. Okay, and this one is important in many cases, in fact.
I was a little confused about what. So, I mean, in the finite data case, for instance, you have this Kullback-Leibler divergence in the lifted space, in the new lifted space, and you have the normal Kullback-Leibler divergence. They coincide. Why would you do computations in the lifted space rather than the original? Because
in the original space, you need to do density estimation. So if I give you data, okay, then I need to estimate P of x, and this itself is complicated.
Okay, so the lifting is something like comes with the smoothing already, yeah?
The lifting comes with the smoothing, and with the lifting, you never compute the density itself. You compute the covariance you compute the covariance matrix essentially, and that's enough information to compute an approximation of entropy.
Are there any other comments, questions?
You had the result where you showed us that if you have your estimate for the d, you get like estimates for exponential moments, right? And if you only use like empirical measures, there has to be some severe restrictions on the underlying measures, right? Because you will never be able, if you have a large class of underlying measures, by just looking at empirical measures to say anything about exponential moments. So what I just didn't understand is, where do the assumptions on the measures come from? Is it, I mean, the setting was a little bit unintuitive for me. So can you say a little bit more like what is somehow hidden in the assumptions on the class of problems that you're looking at?
I think the problem comes from, so I think so let me go back there. So what I can show is that my notion of entropy is sandwiched between the true one and the one of density which are smoothed. Okay, so essentially the way you should see it is that this new entropy is in between the true one and the one with like take your distribution and smooth them by let's say a Gaussian or something. So you use, there's a form of smoothing of the densities which is operating behind the scenes. And so if you do smoothing, then maybe this is solving a few of your problems. So it's not equivalent to entropy after smoothing, but it's between true entropy and true entropy after smoothing. So there's no magic. Okay, so that at the end there's some smoothing of the space which is done by the kernel.
So before we thank our speaker once more, there's two announcements. The first announcement is we're going to have the conference photo taken outside right now, so please quickly make your way downstairs. The second announcement is we'll continue this afternoon, not in this lecture hall, but in a different lecture hall, namely in the room S10. Okay, with this, we'll close the session and thank our speaker once more.